This is Professor Elliott, and in this presentation we are going to take a look at basic oscilloscope measurements. Okay, typical waveforms, part 1. Here we see a sine wave. That's the sinusoidal shape, so it's called a sine wave. And based on the vertical setting of 5 volts per division, that gives us a peak voltage of 10 volts. So the peak is positive 10, or likewise the negative peak would be, of course, minus 10. So 5 volts per division times 2 divisions is 10 volts. Okay, so in this case we have a sine wave with a peak voltage of 10 volts. That gives us a peak-to-peak voltage of 20 volts. Peak-to-peak is always twice the peak. The RMS voltage, VRMS, or stands for root mean square, is 0.707, which is a constant, times the 10 volts. So 10 times 0.707 is 7.07 volts RMS. Okay, in this example we have a sine wave with a peak-to-peak voltage of 4.6 volts. So that means that the peak voltage plus peak and minus peak is 2.3. So positive 2.3 subtract minus 2.3 is an absolute voltage difference of 4.6. And the RMS voltage is the 2.3 volts times the constant 0.707, gives us an RMS of 1.63. So here we see an AC sine wave going into a voltage divider network, R3 and R4, and it has a DC offset being furnished by the 5-volt battery. So in this case, the sine wave will not be centered around 0 volts. Rather, it will be just simply pushed or shoved upwards by positive 5 volts. And we'll see that on the next slide coming up here in a minute. Okay, so here we see our sine wave. It's been pushed up by 5 volts, and we can easily determine that by noting where the negative peak was before the offset and after the offset. And the easiest way to do this practically is to note the change when changing the oscilloscope input coupling to AC and DC. AC, it will look perfectly centered, and on DC it will look like this, just how it actually is. Okay, so here we have a screenshot showing channel 1 displaying a sine wave, and channel 2 displaying the DC offset. So both channels on the oscilloscope do not have to display the same type of waveform. Okay, so here it looks like we're measuring a period. So we have a sine wave which has a period that's between any 2 points where the waveform repeats, and the easiest point to measure is the 0 crossing points, which I've indicated by the dashed blue vertical lines on the screen. And so this has a period of 8.3 milliseconds, which gives us a time of roughly 120.5 hertz. Okay, here we have a square wave, and we have a peak voltage of 10 volts. We have two vertical squares times our vertical setting of 5 volts per division gives us 10 volts peak, or in this case you could also say it's 20 volts peak to peak, but there is no RMS. RMS is only applicable to pure sine waves. Okay, now we're looking at a triangle wave. Again, we left our oscilloscope settings the same. We just changed the signal input. Again, we have 10 volts peak, so it's 2 divisions times 5 volts per division gives us 10 volts peak, or 20 volts peak to peak. Once again, there is no RMS. RMS only applies to normal sine waves. Okay, so here we have a DC battery powering 3 resistors in series. Channel A is measuring the potential, the voltage between its input and ground. So we're essentially measuring VR2 plus VR3, or the voltage drop across R2 and R3. Channel B is measuring the voltage or potential across R3. Okay, so there's a big number at the top. It's in red for a good reason. Be very careful where you're connecting the black clip of your oscilloscope lead. Remember, it is actually earth ground. So do not connect that clip lead, to anything you would not connect the ground. So if you were to take that lead, do not do this, and connect it to the hot lead of the AC source, that's exactly the same thing as jumpering out your duplex receptacle, and you do not want to do that. Okay, so here we're looking at phase angle measurements, and you can see there that remember, time progresses from left to right. So anything to the left occurred earlier in time, and the red channel is signal A, and the B is signal B. So A leads channel B by so many degrees. We'll get to that on the next slide. Okay, so here we have a capacitor and series with a resistor. This is going to give us our phase offset. So really what we're measuring here on channel 1 is E, as indicated. Channel 2 is measuring the voltage across the resistor. And because the voltage and current waveforms in the resistor are in phase, that means essentially we're displaying voltage versus current. This is going to give us a phase offset. Okay. So here we see our voltage and our current waveforms. See, they are not in phase. I know they're not in phase because the peaks or the zero crossings do not line up. Okay. Okay, so here we're getting down to our actual measurements. So we start by determining the number of divisions for one cycle, which in this case is 8.3 divisions. The phase angle theta, which is the phase shift, is the difference between the zero crossings, or the same points on both waveforms. So be sure that you have the both waveforms zeroed at the same reference line. So we have a difference of 0.7 divisions divided by 8.3 divisions times 360.